So why would we want to use the dot product? It's a strange definition. What good does it do? The first important thing that it does is it lets us talk about the length of a vector. Now, as a very simple example to motivate this, let's take a vector in R2. So let's talk about u with components u1 and u2. Sometimes we like to write it as the coordinates of a point, and that allows us to draw a picture. We often represent a vector as an arrow. Why do we want to do that? Well, if you talk about physics class, vectors have size and direction, and that arrow is supposed to encapsulate both of those pieces of information. How long is that arrow? We'll take that to be the definition of the length of a vector. So the length of this vector u, we're going to denote with this symbol, the absolute value of u. Sometimes in other places they put a double bar to talk about it, length or norm. We're going to calculate it with the Pythagorean theorem. When you've got coordinates of a point like this, you can draw yourself a right triangle. There's u1, there's u2, and the length of the vector would be up here. The length of the vector is just going to be the square root of u1 squared plus u2 squared. If we generalize this to Rn, then we'll say that the length of the vector is just the sum of the squares of all the components of the vector. Now, how does this connect to dot product? This is really u1 times u1, u2 times u2, all the way down to un times un, which is the dot product of a vector with itself, and then we take its square root. For example, if I give you a vector w, -6, 4, -3, the length of this vector would simply be the squares of the components all added up, and then you take the square root of the final answer. So you'll end up getting a square root of 61. Some basic properties of the length of a vector. The length of a vector is always going to be greater than or equal to 0 because it's defined in terms of a square root. The output of a square root, we're always going to take it to be the principal square root, so it's always a positive number. Now note, if I tell you that the vector is 0, then the length of this vector is just going to be 0 squared all the way down. So the 0 vector has a length of 0. Now, if I tell you that the length of a vector is 0, now we're asking a slightly different question. Let's talk about the components that I'm going to need in order to make them all add up and square root to 0. I can square both sides of this expression and I'll get a 0. And the only way to make real numbers square and add up to 0 is only if each one of these components is 0. And that means then that the vector itself has to be the 0 vector. So the 0 vector produces a length of 0, and any vector with a length of 0 has to be the 0 vector. Now, the other thing that you should notice is that if you were taking the length of a scalar multiple of some vector, you would just square the individual components. Remember that scalar multiple just means take every component and scale it by some factor c. If we go ahead and we do all this, we can get down to an expression that looks like that. You can split this up. You'll get a u dot u, and so what you'll end up getting is absolute value of c times the length of the vector. A useful application of all of this is something called unit vectors. Now, a unit vector is a vector with a length of 1, or unity. If I take some vector u, it generally has a length that is not 1. It could be anything. So what we would like to do is figure out how to scale it so that its length is 1. So it will have the same direction as some vector u, but a length of 1. If you want to take your vector and turn it into something with a length of 1, you should multiply it by 1 over the length. So you're essentially dividing out the length. U over the absolute value of u gives you the unit vector. So in that previous example, the vector -6, 4, and 3, the length of this thing was square root of 61. So if I want to define some sort of new unit vector, we'll call it v, we're going to take our vector and in terms of numbers and components, take every component and divide it by the length. So just to be really detailed about it, I'm going to do a calculation like this. It's going to be -6 over root 61, 4 over root 61, -3 over root 61. Another application has to do with orientation. How do vectors fit relative to one another? Now I'm going to just start in R2 to illustrate everything. So if I take standard coordinate axes, I'm going to take one vector u, and I'll take some other vector v. Things that mathematicians care about are what is the distance between u and v. You have to define what you mean by distance, but we'll say this length here, from the tip of one vector to the tip of another vector. In order to figure that out, you're going to do a little bit of vector geometry. This would end up being negative v. So if I were to take u and negative v and draw a parallelogram, this is the diagonal. That in the green line should be the same. So this length is going to be equal to d, and that is just going to be the length of the vector u minus v. So the distance between two vectors is just the length of their difference. If we want to get some more information about it, we are going to have to talk about this angle between them. And that's where the orientation part comes in. And to talk about the orientation, we're just going to take those two vectors and look at them in a different way. This distance right here would be the length u minus v. So the length of this side would be u, the length of this side would be v, and now we've got this triangle. You may or may not remember, but the cosine law is something that allows us to connect the lengths of the sides of any triangle. If you have an angle that you know in the triangle, the length of the side opposite to that angle, squared, is going to be the sum of the squares of the lengths of the other two sides, subtract 2 times the product of those lengths times the cosine of the angle between them. And that's why it's called the cosine law. This thing right here is u minus v dotted with u minus v. And then you're essentially squaring the whole thing. If you use the properties of dot product, you're going to get u dotted with u minus v subtracted with v dotted into u minus v. And then you're going to get u dotted with u subtract u dotted with v, subtract v dotted with u plus v dotted with v. That's going to end up giving me u dot u plus v dot v minus 2 into u dot v, because the order doesn't matter. This is u squared, this is v squared, 2 into u dot v. Now, if you clean all of that up and then you plug it back into the cosine law, you'll get length of u squared plus length of v squared minus 2u dot v is equal to length of u squared plus length of v squared minus 2uv cos theta. So very nicely, some things cancel out, and what you're going to be left with is this wonderful geometric interpretation of a dot product. The dot product u dot v could be interpreted as length of u, length of v times the cosine of the angle between them. And this is often what physics people will define the dot product as. They'll start with this as the definition and then work their way to a strange coordinate representation. Why is it the geometric interpretation? Remember that it's in terms of vectors. It's talking about the angle between them. How much of one of the vectors points in the direction of the other? It's talking about this shadow and the length of this shadow. Now, this length right here is u times the cosine of theta. I would like that thing to be as big as possible if I am talking about the vectors being in the same direction. So the largest is when the cosine of theta is equal to 1, and the cosine of theta is going to be equal to 1 when the angle is 0, if these vectors are in the same direction. So v would point one way, and then u would simply point in exactly the same direction. Largest when the vectors are in the same direction. The dot product will be smallest when the cosine of the angle between them is 0. And that's going to happen when the angle is 90 degrees or pi over 2. Now, in terms of relative orientation, there's u and there's v, and the angle between them is 90 degrees. So you're going to have the dot product being smallest when u points in what we'll call the opposite direction to v, when they are in completely opposite directions. Now, you can also reorganize everything here and say that the cosine of theta is going to be u dotted with v over the length of u times the length of v. And it's possible for you to determine the angle between vectors. This is a very key point, that the dot product is a tool or some sort of device that measures if vectors are perpendicular. It has to do with vectors being relative to each other, and this perpendicular idea is important. Now, perpendicular is a word that we reserve for R2 and R3 because we can see what that looks like. But we want to generalize this. Now, when we generalize it to Rn, nobody's ever seen Rn. We can't see if they're actually at a right angle or not. So that we have a new name, we call it orthogonal. We also like to give it a new name because it's going to turn out in math. These ideas apply to things other than vectors and lines. They're going to apply to a whole bunch of stuff. So here's our definition. U and V are orthogonal if their dot product is equal to 0. They are in the most unlike directions they could possibly be in. Now, it's very, very easy to see if vectors are orthogonal. You just take their dot product. And if their dot product ends up giving you a 0, they are orthogonal. If it doesn't, they are not. And in this particular case, if you calculate the dot product, it's equal to 1. These vectors are not orthogonal. Now, orthogonality is the key idea. This is why we bother with the dot product.